Here we introduce and prove the first isomorphism theorem. Alright, so here's the first isomorphism theorem. Let phi be a group homomorphism from groups G to H. Then G mod the kernel is isomorphic to the image. Here, of course, we're going to let K be the kernel to make the proof a little easier to write. So, of course, usually you often state that the kernel of phi is a normal subgroup of G, but we already know that. And that phi of G is a subgroup of H, but we already know that as well. So we're only focusing on this isomorphism part. The book actually goes a little bit further and points out that not only is there this isomorphism, but this isomorphism is a homomorphism that can be written in such a way so that the obvious projection map from G to G mod the kernel factors, so that phi is rho composed with phi hat. And it's obvious if you take this as statement and unwind what it means, that this kind of tells you what this phi hat has to be. Of course, I'm going to call phi hat pi to make life a little easier. What does it have to be? Well, given a coset gk, whatever it's going to map to is going to have to be something so that you get phi of g. So define pi of a coset to be phi of g for some coset representative g. Naturally, because we're looking at the image of phi of g, every element in this codomain here is of the form phi of g for some g, little g. And so this function is automatically surjective. Note here, why is it surjective? Because this is a function from g mod k to the image. But wait, we still have to check that this function we just defined is in fact well defined. Why? Because we defined it on cosets, and the definition we gave the formula we gave uses the coset representative. So we need to check that if you pick a different coset representative, you get the same result. So suppose we have two equal cosets. We need to check that phi of g is equal to phi of g prime. If that's true, then pi of gk is equal to pi of g prime k, and even though our formula depended on g and g prime, it turns out that you get the same answer no matter which element in the coset you picked as the representative. So suppose we have these two cosets are equal, then g prime is an element in this coset. That's one of the equivalent definitions of being equal cosets. Well, that means that g prime can factor as little g times an element in k. So then phi of g prime is phi of g times k. Since phi is itself a homomorphism, this is equal to phi of g times phi of k. Since k is the kernel, phi of k is the identity. And anything times the identity is the other thing. So we get phi of g prime is equal to phi of g. So pi is in fact well defined. It's also not hard to show that it's a homomorphism. If I take pi and I apply it to the product of two cosets, well then it's pi of g prime k. By definition, that is phi of g times g prime. Since phi is a homomorphism, that's phi of g times phi of g prime. But that means that phi of g was just pi of the coset gk. Phi of g prime is pi of g prime k. So we see that pi is multiplicative. Finally, we have to show injectivity. Let gk be an element in the kernel of this homomorphism. Remember, the domain here is a collection of cosets. So an element in this kernel would have to be a coset. What does that mean? To be in the kernel, it means pi of this coset is the identity element in the codomain. By definition of pi of gk, this element is phi of g, because that's the definition of pi. So by transitivity of equality, phi of g is equal to the identity. But if phi of g is equal to the identity, well, by definition of kernel of phi, that means that g is an element in the kernel of phi. But that's the definition of k. So g is an element in k. If g is an element in k, that means this coset is equal to k. So I took an element in the kernel, that was a coset. The kernel of this homomorphism pi, it was a coset. I see which coset it is. It's actually the coset k. So the only element in the kernel is this coset. Remember, we've said before when we studied factor groups, this coset, that is the subgroup, because we're working in the group G mod k. This element is the identity element in this group. So you're saying that your kernel contains only the identity element. And as we've said before, that means your group homomorphism is injective. So we have an injective group homomorphism. It's also surjective. It's also homomorphism. Therefore, it is an isomorphism. And we have G mod k is isomorphic to its image. This one seems like a very strange theorem because the first time you usually encounter it is in modern algebra. A similar theorem actually is true in linear algebra, but in the undergraduate lower level linear algebra course, they don't talk about quotients of vector spaces. But it is true if you have a linear transformation between two vector spaces. The quotient of a vector space by its null space of the linear transformation is isomorphic to the range. And that is actually used implicitly when you prove the rank nullity theorem in linear algebra. You take an m by n matrix and you try to find a basis for the column space. The basis for the column space is actually creating a basis for this quotient space, or this image, which is an interesting fact that they usually don't talk about because this gets way too abstract for a first semester linear algebra course. And it's hard enough to just understand, you know, that if you add up the rank and the nullity of a matrix, you're always going to get n. The other way to look at this is, as I've mentioned before, if you're taking an element over here, y, its preimage is non-empty. I mentioned before, the preimage turns out to actually be a coset. And what this is saying that actually the set of all these preimages is the collection of all the cosets, and actually the group operation is preserved. So you actually get an isomorphism. And so all the group structure gets preserved completely. And this is actually a very useful result. In practice, this gives you a way to handle quotient groups, because as we've seen, quotient groups can sometimes be hard to calculate with. One way to get around that is to replace a quotient group with a more concrete group. This gets around the whole well-definedness issues.